Good morning, good afternoon and good evening. Thank you for joining us today. We welcome you to today's session in Trillium Flow Technologies technical webinar series. My name is Graham Ellis and I am the Valve Product Director of Trillium Flow Technologies UK, and today we'll also be joined by my colleague Adrian Croft, who's our Control Valve Product Manager. Our presentation today will focus on controlling sand erosion in control and choke valves. So throughout this presentation, you'll be able to ask questions. To do this, please use the question box within the Teams broadcast. At the end of this presentation, we will go through any questions that have been raised and hopefully give you some answers. So to a quick overview of Trillium Flow Technology brand portfolio. Our product brand names are synonymous within the pump and valve industry, with pump brands Bergman, Flowway, Gabionetta, Rotorjet, Wemco and WSP. For our valve product brands, we have Atwood and Morel isolation and checks, Autotorque actuators, Batley butterfly valves, Blakeborough control and choke valves, which this webinar will mainly deal with, BDK industrial valve range, Hopkinson's parallel slide and gate and glow valves, Saracen and Sebim safety valves, and lastly tricentric triple offset butterfly valves, all leading names in the industry. Top right picture, we can visualize Trillium's global presence. With a supply chain that spans the globe, our key manufacturing and service centres are located in Canada, China, France, India, Italy, South Korea, UK and the USA. Globally, we have 21 facilities around the world, plus a global network of third-party sales and authorised service centres. Utilising our global presence enables us to tailor the technical and commercial aspects of our products to suit your project needs. Trillium Flow Technologies has a long heritage of innovation spanning 190 years. We are continually adding new products and services to make our customer processes more efficient and productive. Our latest addition to the Trillium family being early 2021 Red Point valves, providing specialist double block and bleeds, monoflanges and associated equipment. So, now for our main presentation, giving a quick introduction to where sand is more likely to occur offshore and discuss some of the effects of sand erosion. Although sand erosion can occur in a number of systems offshore, here we can see a typical FPSO system. Most of the issues with sand erosion can be expected in the wellhead choke valves or around the separator system. Wellhead chokes frequently used to control oil and gas flow rates may experience loss of material due to impingement of solid particles within the extracted fluids. In, for example, a production choke, we see high inlet pressures and possibly high levels of sand. Around the separators, especially the first stage separators, although there tends to be some filtration, then often the level control valve can also be subjected to high levels of sand, therefore still experiencing levels of erosion. We can also come across clean applications where sand is expected to have been filtered away. However, small particles may still linger in the system and continue to cause issues. Let's have a look at some reported issues offshore where the customer advised that the valve could not pass the required flow rate. In the picture on the left, the customer reported that the valve would not close. When they opened the valve, they found that the internal lining of the valve had completely peeled off and the debris had blocked the valve. In the picture on the right, we see another common reason for blockages. Everyone who deals with valve applications will be familiar with the rag, the sponge, the welding and other debris in the valve. In more common control and choke applications, there is at least some filtering of the sand, and usually the sand is a more fine talcum powder than large particles, but this again still causes problems. In some applications, the customer expresses that the fluid is clean. If you have a look at the picture very carefully on the left-hand side, the customer indicated that they felt that there was, why was there erosion? But if you have a quick look at it and a real good look, you can see that there are particles in that fluid. Those are sand. That's what's eroded the valve. The amount of sand in the process fluid can clearly be seen in the picture. However, the customer didn't expect to see that. The centre and the right-hand pictures show the general effect of sand erosion. Sand erosion will tend to leave smooth surface, so it's relatively easy to distinguish from cavitation. I think one of the fundamental building blocks of understanding erosion in control valves is understanding pressure recovery. My colleague Adrian Croft will now go into some detail and describe why that is so important.
Hi, my name's Adrian Croft and I'm product manager at Trillium in Elland. So as Graham says, pressure recovery is very important when considering erosion. So pressure recovery is basically based on this standard graph here, where we see the inlet pressure P1 to the control valve or choke valve, and the outlet pressure P2 to the control or choke valve. The difference between P1 and P2 being the pressure drop or delta P. So what we're trying to do physically is we're trying to drop the pressure from the inlet pressure P1 and we're trying to reach the outlet pressure P2. But in reality, what's happening is as the fluid passes through the valve, then the pressure drops down past the outlet pressure P2 to a point which we call the vena contracta. Once it reaches that point, the fluid expands and we get pressure recovery until ultimately we reach the outlet pressure P2. So if we look at this through the picture on the right hand side, we can see what's happening. The restriction in the line represents the control valve, and what we have is the flow lines of the fluid start to meet the control valve or choke valve. They start to contract, and once they contract through the valve, they reach the point of the vena contracta, and then gradually we get the expansion of the fluid through the valve. So what's happening here is that in dropping pressure, then basically we're generating energy through the valve, and that energy can destroy in some cases, can damage components in others. So if we can minimize the energy through the valve itself, then we can minimize erosion. The other consequence of trying to drive a fluid through this smaller opening is that the velocity accelerates. So as the velocity accelerates, that impingement, if the fluid is dirty, if it's got sand in there, will equally cause erosion of the metallic components. So basically, when we think about pressure recovery, the key thing that we have to consider in the valve itself is how we can minimize that pressure recovery. And in the majority of cases, the cage style valve, which we'll discuss a little bit later, will maintain a low pressure recovery through the valve. So fundamentally, if we want to reduce the energy that's generated by dropping the pressure, then we have to select specific valve trims to enable us to do that. Picture on the right hand side, incidentally, is an axial flow valve, and some valve companies promote these as better for dealing with erosion and contaminated fluids. But equally, this is a picture of one of these trims that's been subject to sand, and clearly it can be seen that the valve trim is highly damaged due to impingement of the sand. So basically, when we're selecting a valve and a valve style for sand applications, then the key thing is to maintain a low pressure recovery. And the valve that will do that is a globe or angle control valve. This fundamentally has the lowest pressure recovery of any valve design on the market. And if we then compare that type of valve, a globe or angle control valve, with, for example, a butterfly valve or ultimately a ball valve, you can see that the pressure recoveries of these valves are much, much higher. So, for example, if the ball valve wasn't completely open, it would tend to erode the surfaces of the ball as the fluid goes through.
So, Adrian, can you discuss more about the effects of velocity?
Yes. So, as we saw before, we've got this typical pressure drop graph. So we get the pressure drop of the fluid through here. And I showed before what happens as we try to squeeze the fluid through a smaller and smaller opening. So quite often a lot of specifications state that valves, control valves, choke valves shouldn't be closed below 10% opening, for example. In some cases, specifications differ. But in general, the reason for this is to maintain a lower velocity. So if we can maintain a lower velocity of the fluid by maintaining a low pressure recovery, then fundamentally those sand particles are not going to impinge at a higher rate as they would typically do with a high pressure recovery trim. So velocity, considering velocity within fluid passages is very, very important. Again, thinking more in depth about velocity, if I take this simple calculation here, what we have is a flow rate of 1,000 meters cubed an hour. We have a diameter of 100 millimeters. And based on that, we can calculate the velocity of the fluid as 35.4 meters per second. If I halve that diameter to 50 millimeters, then the effect on velocity is tremendous. So the velocity goes up by a factor of 4 based on simply reducing the diameter by half. So when we look at flow passages, when we look at the design of the valve trims, then we consider areas, we consider velocities within the valve. And velocities for dirty fluids are different to velocities for clean fluids. So we consider all these factors when we're sizing and selecting a valve. And this here just again gives a general picture of sand erosion. It can clearly be seen, the sand that's gathered on the surface of the valve plug here, and equally on the valve cage. So typically the sand erosion has mostly occurred around the seating point, where the seating point is the point of maximum velocity across the trim. In this case, it could equally have been the point at which the trim was open. So basically, again, I've got to stress that the key thing in terms of handling sand and minimizing the effect of sand is to consider the velocity through the valve trim.
So let's start to take a look at trim design. Can you describe some of the best and worst trim designs to be applied when sand is present?
Sure. So on a low pressure recovery trim, as we previously described, the thing that achieves the low pressure recovery is fundamentally the cage of the valve. So with the cage, what we have is the fluid circulates around the circumference of the cage. And then as it passes into the cage, the fluid collides with jets from the opposing holes of the cage. So all the energy that's formed by dropping the pressure through the trim is absorbed within the opposing jets of the cage. And as it's absorbed, then fundamentally the pressure, the impact of the solids is all minimized in this center section of the trim. And then simply it passes out through the outlet of the trim. In this case here, we've shown an angle valve. So as you can imagine, as the fluid passes out through the trim, the great benefit of using an angle valve is there's no impingement on the body walls, or if there is minimum contact. So when we talk about choke valves or control valves, one of the key factors for minimizing erosion on the body wall and maintaining the pressure envelope is to have a good flow path through the valve. So the majority of choke valves, for example, are specified as angle valves for this very reason. If we consider multi-stage trims now, multi-stage trims with right angle corners are not ideal for applications where sand is present. As you'll see in these top two pictures here, there are two reasons for this. So the green area is generally the flow path that forms with the fluid passing through the trim. So it forms its own natural flow path. So the blue area in the corners of this trim represents stagnant flow. So basically what's happening is the fluid is rotating around on itself. So if we get sand in a process fluid, that sand then can become trapped in these 90-degree corners and the trim can become quickly blocked. Equally, the 90-degree corners can generate and lead to higher velocities around the trim. So these 90-degree corners quickly become smoothed away, certainly when sand is present. So as the flow starts to smooth the corners away, the trim becomes less efficient until eventually the sand bores a hole all the way through the trim. And that's precisely what's happened in this picture down on the bottom right-hand side. What we have is many 90-degree corners within the trim itself, and the brown coloured areas is the sand through the trim, and the sand has simply washed away the trim and completely damaged the effect of the multi-stage. So effectively, in this case, the trim more or less became a single stage trim. So in summary of this slide, essentially you should always avoid 90-degree corners where multi-stage trims are required. So you might say, what's the solution for high pressure drops, high pressure reduction through the valve trim itself? And the answer is essentially our extreme trim. The extreme trim doesn't have 90-degree corners. Instead, it has a smoother flow profile that lets any debris that can get into the trim wash through the trim and exit through into the bore where the plug would be located. So the inlet of the trim, then we've got columns, and these columns are generally larger at the inlet and smaller at the outlet. So as the flow comes into here, the highest pressure drops are where the smallest flow areas are present. So we get the control of the pressure drop through the trim here. It allows the sand, the debris to wash through the trim, but as it's passing through the trim, because these columns are becoming smaller towards the outlet, it means that the flow areas are maximized, and therefore the velocities of the fluid through the trim are reduced as the fluid passes through the trim. And this highlights the fact here that the key differences between a typical Labyrinth trim and our extreme trim. So here in this case, we've got the sand. it could potentially impact on these 90-degree corners, and eventually we could get a whole border all the way through the trim. But equally, it could become trapped in these 90-degree corners so that it could block the trim. Whereas here on the extreme trim, we've got this smoother flow profile through the trim, and it allows the flow of sand to go through much easier, and basically will not block up if sand is present. And just to highlight that fact now, this is a trim which has been built for a sand application. So in the bottom right hand picture we see here, you can see the amount of sand build up on the outside of the trim. You can equally see a large particle that would never pass through any trim that is stuck to the outside of the trim. But here, these are examples of discs within the trim. So you see here, this is a disc from a lower portion of the trim, and we can see some sand erosion around some of the inlet columns. So you can tell the sand is present because it's got a polished surface through the disc. But the big advantage of this trim is it could be completely disassembled. And these are examples of the disc higher up in the trim where there was no sand erosion at all. So simply from a customer point of view, they could replace 2 or 3 discs within the trim, and then the rest of the disc could be reused. And fundamentally, the advantage of this trim to the customer was that we took the life of the existing valve from 6 months up to, say, 6 years. So everything eventually will start to be eroded when sand is present. Nothing can withstand sand erosion. But the key and fundamental to what we have is that we can extend the life of components. We can extend the life of valve internals so that we can get a longer life out of the valve itself. The other thing with the extreme, also shown in this picture on the bottom left, is that rather than a single flow path, what we have is a flow path that impinges together. So this impingement effect also helps us to reduce the pressure of the fluid through the trim with minimum effect on material surfaces. In this slide, it just shows an example between a Labyrinth trim and the extreme trim. So there are a few things to note here. The Labyrinth trim has what we call a single flow path. So there is no interaction of the jets as it goes through the trim itself. And what we have here is the ends of the 90-degree bends have started to erode. So instead of them being true 90-degree bends, these are now rounded, and basically we have the start of erosion. The other thing that you'll notice is that these were both on the same application, but here we've got a relatively small plug diameter in the center, whereas here on the extreme we have a much larger plug diameter. The benefit of that is, first of all, we can get a higher CV through the extreme because we're relying on the jetter interaction to give us the additional pressure drop. But the second thing to consider is stepping back to the comment on velocity. With this smaller opening here, you get higher velocity across the trim, across the plug itself, whereas here on the extreme, you have a much lower velocity because fundamentally the area is much bigger.
So tungsten carbide trims are fundamental to combating sand erosion. Adrian, can you discuss some of the features of tungsten carbide, some of the do's and don'ts when using the material? And can you also advise if extreme trim can be supplied in tungsten carbide?
Yes, tungsten carbide in the oil and gas industry is fundamental on many valves where sand is present. It would only be on really low sand applications where we wouldn't fit tungsten carbide. So on our designs, this is typical to our control and choke valves, we would mount the tungsten carbide within steel holders and steel sleeves. So for example, on a cage here, the tungsten carbide's sleeve would be shrunk into the steel holder. Equally, the tungsten carbide nose would be inserted on a steel holder in the plug, and the tungsten carbide would be inserted into a steel holder on the seat ring. And the reason for that is tungsten carbide is really, really brittle. In simple terms, you can imagine it like a tile in a bathroom. So that a tile in a bathroom is very resistant to scratching or damage. But if you dropped it on the floor, that tile would typically shatter into 1,000 pieces. And this is the same with tungsten carbide. If something hits it at high velocity, potentially that tungsten carbide would shatter. So the key thing with holding it in steel housings is, for example, this cage, this steel cage, would prevent any direct impact of any large particulates. So Graham talked about the welding rods, and occasionally it's nuts and bolts within the pipe. If they're hit at high velocity, would potentially shatter the tungsten carbide. So some valve companies call this a brick stopper. There are different terminology across the industry, but typically one of the key benefits of holding the carbide into a steel housing is to prevent the impact. It's not to say that we can't provide solid tungsten carbide components. We can, and we have done many times in the past where customers demand it. But in our opinion, this design and this application is best for protection of the carbide. So talked about shattering and failure of the carbide. This gives you an example of precisely that issue. When we're dealing with process fluids, liquid process fluids, then there is another factor that we've got to take into account where we get high pressure drops typically, and that is cavitation. Cavitation is very, very damaging to tungsten carbide for two reasons. The first reason is that tungsten carbide is basically held together with a binder. That binder, in simple terms, if we call it a glue. When cavitation is present, then cavitation basically eats away at the glue that holds the carbide particles together, and it would destroy some of the surfaces. The other big effect of cavitation, if it is present, is it sets up vibration and shock waves throughout the valve trim. And those vibrations and shock waves, again, from the example of the bathroom tile, can induce failures and cracks in the tungsten carbide. And this is precisely what's happened here, where the valve plug has failed and shattered, and the carbide has totally failed. So much so that in this case, the valve had to be stripped down and the parts completely replaced. So what can we do with cavitation? And the answer really is we've got to totally eliminate it before we install a tungsten carbide trim. And the good news is that cavitation can always be eliminated. So cavitation can be eliminated by the application of multi-stage trims. Multi-stage trims can also handle high pressure drops. So again, where velocity is being dealt with, then we can also apply multi-stage trims. So when we look at the extreme trim that I've already discussed, how do we actually apply it with tungsten carbide? Again, it's very, very brittle. So if we tried to manufacture it, for example, as a thin plate in 3mm sections, that plate would just crack and fail. So what we've got to do is adapt the design as we see here. So the design of the tungsten carbide discs or plates is, in this case, 10mm thick. If they're smaller valves, we may go down to 6mm thick, but fundamentally they're much thicker sections being tungsten carbide than we would have for a typical standard extreme disc in metal. The tungsten carbide discs themselves are then assembled as a stack and then glued or unitized together into a complete stack. And in this case, they were inserted into the valve in a steel holder, again to give us additional support and an additional protection for the carbide. So the example here is a main oil line valve, MOL valve, and again, as Graham pointed out, this is a valve where you wouldn't expect much sand, but in this case it was, and the customer wanted a solution for the sand that was in the valve itself.
What's your opinion about using globe valve bodies when sand is present? And also, if you feel that a globe valve is not the most suitable style, can you discuss what the preferred style would be?
Yes, if we think about a globe valve, as I said before, the trajectory of the fluid as it goes through the globe valve is that the fluid comes in through the inlet, passes around the valve cage so that it fully circles around the cage, and then passes down through the outlet. So within the trim itself, we've no great issues within the trim, but the one important point within the valve itself is the globe shape. And as we get sand impingement here, then basically we can get a failure of the pressure envelope within the valve itself. And that pressure envelope, of course, is a key safety area. If we, for example, we get oil leaks on an offshore application, then that can cause all sorts of issues with health and safety. So what we can do, rather than just having, if a globe valve is required, what we can do rather than just having the pure shape of the globe being or taking the impact of the sand, is we can fit a seat diffuser. So this basically fits under the seat of the valve trim. It has a solid base, and the base itself would usually be hardened with something like stellite. So what happens is the fluid would pass down here, it would be hit the base, and then it would come out of the holes within the diffuser and basically diffuse the flow. And this picture here on the right hand side just shows you some of the effects of erosion, and in this particular case here you can see that the dipenetrant has been applied to the body so that we in a very short period of time there would be a penetration of the pressure envelope. So basically, as I said before, as touched on before, the best solution for valves or choke valves is an angle valve when sand is present. So with the angle valve, what we have is the fluid coming in from the left-hand side here. Again, it circulates around the circumference of the valve cage and then simply passes down through the outlet of the valve. There's minimum contact with any portion of the walls of the valve body. But if there was, we could fit some additional protection of a sleeve within the outlet of the valve. So the sleeve would serve to protect the pressure envelope. We could also look at minimizing any effects of changes in section, not 90-degree corners, but angles within the outlet of the valve, so that again the fluid has a much smoother trajectory through the valve and through the outlet of the valve.
Apart from using tungsten carbide, is there anything else that can be done with the valve plug seat design to reduce the rate of erosion?
So on a conventional control valve plug and seat, this is shown here, and typically what we have on the valve plug is we have an angled connection on the valve plug That then contacts the seat, so we get a point connection on the seat. But as the valve plug then lifts up, the fluid can then pass through between the plug and the seat. And if the plug is close to the opening of the valve, then this can potentially cause a higher velocity across the valve trim. And ultimately, this impingement of the fluid, the solid particles, can generate erosion of the seat, so that ultimately next time the valve is closed, you don't get a tight closure, and then that equally can lead to further erosion. So considering the seating point, the seat angle is very important. And also considering how the leakage is defined. If the valve's going to be closed for significant periods, then what we can have is the fluid passing between the plug and the cage. And if, for example, there's a small leak within the valve, across the valve trim, then that leak, when sand is present, can propagate so that we get erosion of the plug and we get erosion of the seat. And as that then expands, we then get more erosion. If this is the seat diffuser, then we get microjets of fluid passing down through the outlet and generating erosion in the outlet of the valve. So how do we deal with that? And the answer is that we can fit a special plug in a special seat to deal with sand impingement. Basically, rather than an angled contact, what we now have is what we call a protected seat. So the protected seat has a lip on here, so that there's no direct impingement of the process fluid as it passes through the trim. The other key effect is because the plug has to lift further away from the seat to be able to pass the fluid through the valve trim, then basically what that means is we can reduce the velocity of the trim, and again, reducing velocity is important for minimizing the effect of erosion when sand is present. So basically, yes, we can do things with the trim design, with the valve plug, with the seat. We can add additional features for redirecting the flow partially through the valve trim to minimize the impingement. All these things are possible once we specify the valve. So in specifying the valve, in selecting a valve and a valve trim where sand is present, specification, knowing how much sand is present is all important for proper selection of the valve and the valve trim.
So Trillium have supplied special designs for specific customer applications. Adrian, could you give some details about these designs?
Yeah, so just to have a look at one particular application, something special, very close to my heart, in Denmark. And basically we had a customer who wanted a valve that could be used for both production purposes and for water injection. So basically for production purposes, they're taking the oil, the gas out of the ground. But for water injection applications, they're injecting water the opposite way through the valve. And the reason for that is because in later life, they lose pressure in the well, so they have to inject water into the well to maintain production. So basically here we had to first of all design a valve trim to eliminate cavitation through water injection. So we had to specify the correct number of stages for the valve to eliminate cavitation, but equally we had to have relatively large flow passages so that we minimize the effects of blockage due to sand. So how did we do that? How did we physically achieve that? What we did was we had one stage of pressure reduction within the valve cage itself. And this lighter blue stroke grey area is physically the tungsten carbide within the cage itself. But we also put a second stage of pressure reduction within the plug nose. And having two stages of pressure reduction basically meant we could eliminate the cavitation. But more important, when the valve was used for production purposes, it allowed the sand to pass through the trim, and simply lifting the plug uncovered more holes. But where the customer expected large slugs of sand, for example, then we fitted these or installed these large slots here, so that these large slots could be lifted out of the way of the fluid to allow any large slugs of sand to pass through the trim. We also put scraper rings in there, designed the valve for bidirectional flow, so a highly complex valve to provide a specific solution for the customer.
Adrian, on one project, I remember we produced a special customer design application where we did some sand modelling. Can you give a quick overview?
Yes, another customer solution here, this time offshore UK. And this was a very, very specific choke valve application. The actual valve that was produced is shown here. But basically we had the requirement from the customer, who was very concerned about the collapse of tungsten carbide trims. So the customer basically wanted some security in terms of knowing that there wouldn't be too much flow passing through the valve. So he wanted an additional flow limiter installing in the valve. And when we got the order for this valve, and we got the order also to produce sand modelling, we found out that we were the only people, the only valve company that could produce such a valve to meet the customer requirements. And if you can see here, this flow limiting device was basically fitted under the conventional trim. And in simple terms, it was a small orifice, but we had to go through many iterations to determine the best solution for the customer and for modelling of the valve trim. So the two slides that were coming up are just showing one portion of sand modelling, but there were many, many more iterations of these physical models. So basically what you can see here is the sand passing through the valve is coming in from the left-hand side, and this model basically shows how the sand would circulate around the upper portion of the valve body before it passes into the cage. Then we modelled how it would pass through the valve trim and how it would pass through the flow limiting device. So in passing through the flow limiting device, we could look at how the sand would erode the limiter, how it would erode the valve trim, and we could further do some prediction modelling for this customer to say that the lifespan of the valve trim would be X amount of time before he had to replace the parts. So all those formulas, all those determinations of how much erosion is going to be is based on standards. And basically, again, we were unique in terms of being the only valve company that could provide this type of modelling. So Graham, a question for you. We can also print the extreme trims. Do you want to give an explanation of how we do this and give an introduction to this in our portfolio?
Thank you, Adrian. So yes, up to 2016, all extreme trims were manufactured by Spark Erosion. In simple terms, a spark is formed between a tool and a disc metal. Moving the tool starts to erode the disc to form the complex shape of the extreme disc flows. Now, this does have some advantages. It's very accurate in complex geometry, and it gives smooth flow paths. However, there are some disadvantages. Each disc needs to be produced individually. That leads to long run times, and stacks must be assembled by using welding or clamping. Now, with 3D printing technology called additive manufacture, we can generate complex shapes directly from 3D CAD models. Additive manufacture using these CAD drawings or 3D object scanners to directly deposit material layer upon layer in precise geometric shapes. As it implies, additive manufacture adds material to create an object, doing away with traditional methods of milling, machining, shaping, or other means. For our extreme trim, we would produce a complete disc stack in one additive manufacture process. Each disc would not be individually printed. But here we see a section through a disc where through the 3D printing, we're able to form more complex shapes. In this example, we have introduced aerofoils onto the inlet and outlet columns. These aerofoils help to give a smoothing of the flow. So to recap, the benefits of additive manufacture: complex parts can be manufactured using additive manufacture effectively, certainly faster, potentially cheaper. Lead time reductions as no assembly is required. The assembly would have multiple, normally with old traditional methods, you would have more than one component put together. Using additive manufacture, you're able to do it in one manufacturing process. And less waste is generated because you're only printing the material required for the product that's being created. So we're getting to near the question times now. So just a few more minutes to get your questions in. But just before I do, let me just do a couple of questions to start the ball going. So first question, as an operator, what are the benefits to me in dealing with sand erosion? The key thing to remember is when sand is present, parts will erode, but by careful valve selection, you can significantly increase the life of the valve. So for example, extending the life of trim from 6 months to 5 years. This will mean 10 times less service intervals, less plant downtime, more production or no interruptions to production, less service man hours, planned service intervals rather than reactive or emergency situations. So another typical question that we get asked, you've given a lot of detail in this presentation. Can you briefly state what would be your typical offering as a best solution? Well, obviously, there are many factors to take into account when selecting the best valve solution. Where there are concerns and known sand content, it's best to discuss with our sales application team. In general, it's largely depending on the pressure drop and the amount of sand. We would most normally recommend our Tungsten Carbide multi-flow trim or our extreme trims. These provide the best flow path through the valve, reducing erosion and blockages.
So just looking at some of the questions now that come in. First of all, one here, there are many valve suppliers in the market. Why do you think your solutions are better than your competitors? So overall, then the key thing here is that our solutions are high technology solutions. So our valves are specifically for control and choke applications. They wouldn't be used onshore, for example. So if we had a wellhead in the desert, these typically just use low technology choke valves. They're very, very cheap. If there's an issue with the valve, then basically they would unbolt the valve, throw it away, and get a new valve. What we're talking about here is specific control and choke valves that are specific to offshore, usually applications where we have to control with minimum erosion, minimum downtime, and basically have the longevity of the valve that customers demand. Another question here is, one of your competitors uses an outside sleeve design of choke valve. Why is your valve better? And although I can't show a picture of an outside sleeve choke valve, essentially to describe it, what we have on an outside sleeve is basically the plug runs on the outside of the cage. And the reason for that is to minimize impingement of the fluid within the center of the trim. But in doing that, it brings many other issues with the valve design. And some of those are to do with, first of all, the tungsten carbide is exposed on the outside of the trim. So if we did get some of those welding rods or nuts, bolts that sometimes pass downstream, the tungsten carbide, if it got impacted by these components, could potentially collapse. Within these designs as well, it's very difficult to install multi-stages. So the multi-stages are built out from the center of the trim, but they're not multi-stages as we've shown for the extreme trim. They're just simple, relatively high pressure recovery trims. So again, fundamentally, the outside sleeve valve is a high pressure recovery trim. And finally, on this design, then the one big factor with these valves is that they're usually subjected to high levels of vibration. So where we have high levels of vibration, then again, from the tungsten carbide point of view, then those high levels of vibration can cause damage to the trim. Another question here is, on valves with small CVs, is there any difference to trim selection? And the answer is yes. Although we've not specifically covered it within this presentation itself because of constraints of time, then when we're dealing with small CVs, consequently we have to have small flow passages. So we have a trim which we call a spline trim, and we manufacture that spline trim with a V-notch groove on there, but we have to take account of the size or the potential size of the sand particles that are going through the valve trim. And in doing that, we can ensure, first of all, that we manufacture the spline in tungsten carbide, and secondly, that the trim itself won't get blocked up. So so yes, we can do it. We just have to look at the trim and the trim design more specifically. Another question, do you ever get involved in supplying trims to retrofit into your competitors' valves? Yes, we do. It's not always the easiest thing to do, and there are certain times when you wouldn't do it, but yes, we can do it. So let's cover the times that you wouldn't do it. Basically, if it was, for example, a low-cost, small carbon steel valve, then it's not worth spending the time to retrofit a trim within an existing valve body, provided the body can be extracted from the line. it would be simpler and probably a lower cost simply to replace the complete valve. But where, for example, we have a much larger valve, let's say it's in super duplex, so fundamentally you've got a high integrity, highly expensive pressure envelope, then it does become economical to be able to replace the trim. And for example, we can fit the cage trim, we can fit the extreme trim. The thing that we've got to do in this case is work with the customer. We've got to be able to establish the dimensions of the internal components of the valve, and then we've got to go away, design our trim and supply it and fit it within the valve itself. So yes, we can, but again, we have to work with the customer to basically come up with a solution. Another question here is, extreme manufactured using 3D printing technology, is it possible to replace the one disc stack by welding? If it gets eroded, when the valve is in service. With a 3D printing, as Graham pointed out, then what we can do is rather than replacing the disc stack, one thing that hasn't been touched on is our disc stacks are reversible. So for example, offshore in Scotland last year, we had a customer that hadn't ordered spares for the valve itself, but what they did is when they opened the valve, they found they had some sand erosion within the trim. And rather than having an emergency situation where they had to run around, get new components for the trim, then what they did was basically reverse the extreme trim, so that in reversing the extreme trim, I said before that it's only the lower discs that tend to get damaged because of velocity. In reversing it, the upper discs became the lower discs, and consequently they could use the valve. It actually extended the life of the valve a significant amount of time, and when I say significant, much longer than they expected, and that then gave them time to order spares and replacement parts. Another question, is the range of sand particle size usually included in the project specification? And sometimes that's very much a mixed bag. Some customers have detailed information on sand and particle size, whereas other users, other customers, until they actually drill the well, until they open the valve, they have no idea what amount of sand and what size the particles are going to be. As Graham said, there's usually a significant amount of filtration of the sand, but when we're dealing with the separators, the first stage separators, certainly the test separators, then it's one of those unknown factors in many offshore applications about how much sand we would get. One of the early pictures that we saw, as Graham pointed out, that is an application where the customer expressed that the fluid was clean, and they basically came to us and said, your valve's leaking. And it was only when they then showed us the photos of the valve that we could establish that they had significant amount of carryover from the sand that is present in the fluid. So not always known when the process starts up. Some processes can have carryover, which is unexpected. So sometimes there are these situations, certainly offshore, where unexpected events occur, and we've got to be able to deal with them and deal with them in a timely manner and provide solutions to the customer. So that basically answers all the questions that have come in. Graham, I'll hand back to you to close out this session, if that's okay.
Thank you, Adrian. We have now come to the end of our presentation. We thank all those that have attended today's webinar, and we thank you for listening. If you have any questions, please use the info@trilliumflow.com. You can address it to Adrian or myself, and it will soon find its way to us. There will be further Trillium webinars available over the coming weeks, and if you checked out our Trillium LinkedIn accounts, you'll see when they're next happening. Lastly, this webinar will be available on YouTube in the coming days, so please check out Trillium Flow Technologies YouTube account. Enjoy the rest of your day, stay safe, and thank you very much.